Welcome, and we will look at backpropagation algorithm. So, let us understand some key issues of this. You get a correct answer which is quite rare. You can hope to get the best or an optimal answer over 10,000 to 20,000 epochs or iterations. Since these are all learning algorithms, learning is always slow and steady, meaning initially large error. In most cases an answer means small or very small error. In fact, most engineering and life problems means good answer implies low or even acceptable error. Nobody says error free. Okay. So, the issue is having a knowledge of the error which is large in beginning can we lower or minimize the error. For what? So that we reach this. We want to reach that state. So, how do we do it? Let us see what we know. We know an input x. We have multi-layer perceptron here. We get an output y. We know initially y is the correct answer, let us say. Initially we get a very low version of this, we call it y cap, okay, y hat or y cap, and y cap minus y will be the error. We must do something over epochs or in your terminology iterations. Iterations such that y cap tends to y, which results in y minus y cap tending to 0, basically error tending to 0. So, the idea is quite simple. This has come from Widrow's and in fact Widrow and Hoff adaptive algorithms idea. This also comes from Gauss results on least mean square. So, look at y minus y cap, which is error, but not E, but E squared, square the error. E can be positive or negative, but E squared is always greater than or equal to 0. Not only that, E squared is even symmetric. Which not reachable to 0. This is the minimum error, E min. In this case, E min is 0. To minimize basically minima or maxima, I want the first derivative of that dE by d whatever variable alpha to be 0. Now, this dE by d alpha, if alpha is a parameter, this is actually slope or gradient, like this at this point, gradient. Suppose instead of this I do this, I calculate the gradient but move in this direction. This is called gradient descent. You are descending down the gradient which will reach the minima. This is all the idea, which is actually used in adaptive filters, where they do the following. You have a filter with weights W1, W2, etc., Wn, and you all have delays. These are output y, this is your input x. What you do initially is you do not get the correct answer, you have a y reference, which is ideal case. You do y minus y reference, error is y minus y reference. You square the error, so this is E squared, and you use an algorithm related to this which will work like a potentiometer changing the weights W1, W2, Wn such that when E squared is minimum, you have W1 optimal, W2 optimal, etc. So, you have all the weights optimal, and it would have started initially randomly or even very low value 0.01, 0.001, etc., etc., not 0 of course. So, you update. So, basically you want new weight is equal to old weight plus update. This is the algorithm which is used even in your multi-layer perceptron as follows. So, basically I need knowledge of error, I want the square of the error because I want to calculate the gradient consistently, and the square of that error function is convex and it allows me to calculate the gradient. All this is actually put in a slightly different way for multi-layer perceptron as follows. So, error is a function of weights. For example, Wij for all I equal 1 to n, j equal to 1 to n. So, what is back propagation? You are calculating the error at the output layer. This is your input layer x. You are calculating the error as y minus y cap. What initially you get in the first iteration is y cap. What you wanted as y, calculate error, square the error, what you get is e squared. Now you do the following. You find out the rate of change of this function. It is also sometimes called loss function with respect to various weights. Each weight is influenced. You calculate the variation for the output most layer, propagate that back to inner and inner layers up to the first layer. Again do this. That is why you call it epoch rather than a iteration. You do that repeatedly, sometimes as much as 10,000 to 1 lakh epoch, and it will slowly converge. Please remember, this is very slow, but when it converges very well. Okay. So, we will just look at a few simple calculation for that. So, we have this, I will not go into internal structures. Okay. I have a bias term B which has a W naught 1, the other input is X with weight W, call it W1 X1. So, you have W1 X1 plus B is your Y. If the answer was correct, in the first step the answer will look like as Y cap is equal to Wx plus B, which needs to be iterated. Okay. Your actual correct answer is Y. Y minus Y cap is error, which is Y minus of Wx plus B, and I want the square of this. This is your loss function L. Square of the error is loss function. So, I want a gradient delta L by delta W. This is only one weight, we will do for multiple weights. So, which is delta of delta W of Y minus Wx minus B the whole square. We also know partial derivatives delta L by delta W is equal to delta L by delta E into delta E by delta W. This is your famous chain rule. I want to caution you now here, when you look at multiple layers, the chain rule extends over multiple functions. That is the reason why you do a topic like multivariable calculus. Okay. What is delta L by delta E of E squared? That is 2E. What is delta E by delta W? Is equal to minus X. Therefore, delta L by delta W is equal to 2 times E into minus X, which is equal to minus 2X into E, which is equal to minus 2X into Y minus Wx minus B. Similarly, I can do the following. What is delta L by delta B? Is equal to delta L by delta E into delta E by delta B. Delta by delta B of Y minus Wx minus B, which is equal to minus 1. What is delta L by delta B? 2E into minus 1, which is minus 2 into Y minus Wx minus B. So, the gradient is minus 2x into Y minus Wx minus B minus 2 into Y minus Wx minus B, which will give me minus 2x Y minus Y cap minus 2 into Y minus Y cap, which is same as minus 2xe minus 2e. So, how do we update now? We update now. Delta W is equal to minus delta L by delta W, and the new W can be W old plus delta W. Similarly, delta B is equal to minus delta L by delta B, which is again, so B new can be put as B old plus delta B. Normally, we choose delta W to be minus alpha times delta L by delta W, and this alpha is called the learning rate. They also use words like momentum and stuff like that. Normally a small value like 0.01. So, we can accelerate, we can do like fast stepping and all that, but we may miss critical learning if we do not go at optimum rate. Going too fast will not help, going too slow also will not help. Okay. Similarly, delta B is equal to minus alpha times delta L by delta B. We again now the last function looks like Y minus W new X minus B new whole squared. Do this till the following, till loss is less than some threshold, or you reach acceptable limit. Stop. This is how the algorithm works for one weight. We will just see quickly for multiple weights across multiple layers, then you will get a feel for clearly what is happening. So, the back propagation algorithm will connect input, we have X, we have one neuron with an input like input part A and activation Z1 and A1, it goes to another neuron which is having a input process Z and activation function A2, I get a Y. Okay. The single neuron will have W1 weight and bias B1, this will have W2 B2. The error is as usual y minus estimated value at first iteration y cap, and the loss function is square of the error. So, we need to calculate delta L by delta W2, delta L by delta B2. We have to calculate this first because it is propagating towards the input layer, followed by delta L by delta W1 and delta L by delta B1. Delta L by delta W2 is equal to delta L by delta E into delta E by delta y cap and delta y cap by delta Z2 into delta Z2 by delta W2. 4 partial derivatives. Similarly, delta L by delta B2 is delta L by delta E into delta E by delta y cap into delta y cap by delta B2 into delta y2 delta Z, Z2 delta Z2, I am sorry. Delta Z2 by delta B2. And based on this, delta W2 is W2, that is delta new plus delta W2 old. Similarly, delta B2 update is original B2 plus delta B2 old. So, you do the same for delta L by delta W1, delta L by delta B1. So, this idea of back propagation is really sequence of computation, from input to loss function, if it is differentiable, that is very important, differentiable at every step. every step we can compute the gradient of loss function. Given the gradient, we can update weight and bias. So, it is not an easy problem because you are calculating the square of the error with respect to each layer Wij, 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 Wij. This is 1 to 2, this is 2 to 3, this is n minus 2 to n minus 1 layer, this is n minus 1 to nth layer. So, at every step weights Wij and Bi, B or Bi or Bj at each layer has to be updated. So, one does not know whether they all converge or few layers converge first and then slowly, like adaptive filters where the most significant bits converge first, then the coarse setting gets first and then the fine setting happens. This is the way the backpropagation algorithm works. You have to compute partial derivatives, almost a million partial derivatives for a layer, typically 100 to 200 layer machines with typically 100 to 200 neurons in each layer. This is deep learning. Deep learning is 100 to 200 layers which will have 100 to 200 neurons in each layer or even up to 1000 layers, 1000 neurons in each layer. And the most important thing is it could be fully connected or partially connected. So, fully connected and partially connected look like this. This is fully connected. Partially connected, whatever. So, some of these connections, some of these Wij are 0, not connected. Okay. It depends how, and in fact many times all the outputs can be, you can have a single output. Suppose you have character recognition 0 to 9, you will have 10 outputs. This stands for 0, this stands for 1, etc. and the last one stands for 9. So, it depends how many classes you think are the problem at the output, etc., etc. All said and done, millions of partial derivative, millions of partial derivative. So, look at code, there is a special code for this, it is called CUDA for machine learning and deep learning. We will now summarize. So, we looked at threshold logic, then we looked at a elementary neuron, we classified better by looking at perceptron. We also saw that perceptron is equivalent to one line. When I say line, line in 2 dimension, hyperline in 3 dimension, and n minus 1 dimension hyperline in n dimension, one line separator or basically a classifier. We understood that complicated data classification can be done by 3 layers. Real learning happened when perceptrons were interconnected. Multi-layer perceptron is the key architecture for machine learning or deep learning, more so deep learning, which is only done with neural net. And multi-layer perceptron is equivalent to today a backpropagation algorithm which involves partial derivative of loss function with respect to weights at every layer and backpropagation algorithm is very effective if continuous function across layers. That is the reason why you do not use hard limiter and other things, but you tend to use sigmoid functions or Gaussian functions in activations across. There are other flavors where it also uses knowledge of conditional probability, which is called the Bayes net. Will not, but this is good enough to begin with. Okay. Okay, thank you. And for all of machine learning or deep learning neural net, we have used this book called Why Machines Learn by an interesting author, Anil Ananthaswamy. You should read this book because it is the entire story of machine learning, starting from threshold logic all the way to Hinton's work. Hinton's work on real deep learning. So, almost 80 years of neural network, machine learning, deep learning has been done, covered well. Almost at class 12 level math plus little linear algebra. Yeah, Only way to learn machine learning is to implement. Before implementing, read, implement small size, about 4 layers with 5 to 6 neurons in each layer. Then use CUDA code for whatever full size problem. Thank you.